Hi, my name is Ralf Bachmayer. I'm an associate professor here at the Faculty of Engineering and Applied Sciences, and I want to describe a little bit my research that is enabled through the Petro-Canada Young Innovator Award that I've received in 2009. I'm working in general on autonomous underwater vehicles that are pre-programmed. They don't have a cable with it, no tether, and you send them off and they go on for hours, days, weeks, and sometimes even months under the ocean and collect data and information for scientists and offshore operators, for example. So this award will help me, and has already started to help me, develop a hybrid glider. That's a glider that has, besides its usual propulsion module, which I get to in a second, a propeller on the back that can fold and unfold if needed. The glider, as I said earlier, is basically a AUV, autonomous underwater vehicle, that propels itself by changing its weight in water from light to heavy, and so has wings sticking out on the side that propels it in a sawtooth kind of pattern back and forth. It has a rudder, so you can control also the direction it's moving in, and it collects data on its way. Usually basic data is conductivity, temperature, and density information, which is a basic kind of measurement for physical oceanographers. What we have done in the past, we have adopted other sensors into that system, and we currently work on current profiling and some optical measurements with these gliders while they're on a mission. The gliders are a commercial product that you can buy from several companies, mostly in the United States, and we are using those to develop other solutions, basically to expand the envelope of operation, and in particular with a view on what the needs are in our region here, basically in the offshore industry, but also in terms of ice kind of deployments, which is kind of a particular interest of me more recently. So the gliders we have are Slocum gliders. They go to 200 meters of depth. They can stay out in the ocean for a month and collect the data. They move extremely slow through the water, roughly half a knot, a little bit above that, 30 centimeters a second in the horizontal, which allows them to go actually that long, because your endurance goes up the slower you move. However, you're very susceptible to ocean currents. So if a current is opposing you, you might not go anywhere else. So one of the ideas of the hybrid glider is to actually put a propulsion module on it that basically turbo boosts the glider through a current that's only temporarily or in a spatial kind of constraint, and once you don't need it anymore, you turn it off. The other reason to have a hybrid glider with propulsion module on it would be to fly horizontally. As I described earlier, the gliders have to move in a sawtooth pattern in order to propel themselves forward. By putting a propulsion module on it, we can move horizontally and collect data that way. One of the examples, for example, would be ice profiling. We have ice profiling sonar that measures basically the distance from the glider to a reflector in the water column above, which usually is the surface water to the air interface, but in the presence of ice, we get a reflection back from the ice and can therefore, together with the depth of the vehicle, determine how much the ice penetrates into the water. So that's the idea behind the ice profiling. If you want to do that over a longer stretch, you don't want to necessarily go up and down. You want to actually continuously fly on one level and measure just your distance, and therefore get kind of a track of the ice at the surface and how thick that actually is. You can combine that with other measurements that are airborne, and you can then come up with the ice thickness model, which is very interesting for the offshore operators because it allows them to shut down or turn on their production facility. Again, depending on the ice thickness, they're restricted by that. But also for climate research. The climate researchers are interested, how does the ice thickness actually change over time? And when you do a drill, you drill at one point, but you're talking about a huge area. So if you can provide a track of ice thickness, that's a huge step forward in providing more information about how this profile actually looks like. Another application would be iceberg profiling. If you have an iceberg drifting into an area that is sensitive to scouring, which means basically the iceberg ripping up the seafloor, you want to know how deep is this iceberg. the glider could give you potentially a first estimate of the depth of this iceberg, and then warning you there's something coming your way that you might have a closer look at. And then other sensors can be deployed to do actually very accurate kind of almost imaging of this iceberg. More recently, we have come up with a couple of other issues. Marine protected areas worldwide are getting more and more into the interest of the public, and there's a group in Sydney, Australia, that wants to develop a low power imaging module. We would like to combine that with them into a low power kind of imaging and underwater vehicle platform to bring back pictures of the seafloor, look at the ecosystem, and look into how that changes over time based on fisheries activities, but also other changes in the environment. So there's a lot of opportunities that have opened up through this funded project now, and we are very excited about the possibilities we have with that now.